In this video, we're going to develop some formulas that are useful for doing applications of the dot product and the cross product. So first, we're going to show that the area of a parallelogram determined by the vectors A and B is equal to the magnitude of the cross product of A and B. So first, let's imagine the parallelogram formed by the vectors A and B. So A and B are shown here. We complete the parallelogram and we have that shown in front of you. Now we have a height of a parallelogram shown on the diagram. And we know that the area of a parallelogram is equal to base times height. So the area of this parallelogram will be equal to the magnitude of vector A times the height. Now, we know that the height will equal the magnitude of vector B times the sine of theta. The reason we know that is because using SOHCAHTOA, we know that the sine of theta will be equal to opposite over hypotenuse. And so switching it around just a bit, we see that H will be equal to the magnitude of B times sine theta, which is what's stated right here. Now, that means that the area of the parallelogram, since we know it to be the magnitude of A times H, will equal the magnitude of A times the magnitude of B sine theta, because, like we said, H is equal to the magnitude of B sine theta. Let's keep that as equation 1. We'll keep that in the back of our minds. Perhaps even write it on a sheet of paper if you're following along. Area equals magnitude of A, magnitude of B sine theta. Area of a parallelogram, that is. Now we're going to do a little bit of other seemingly unrelated work, but we're going to bring it around to show that it's relevant to the work we just did. Let's determine the magnitude of A cross B. Well, we know that A cross B is equal to the vector shown, A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, A1B2 minus A2B1. That means the magnitude of A cross B quantity squared will be equal to A2B3 minus A3B2 quantity squared plus A3B1 minus A1B3 quantity squared plus A1B2 minus A2B1 quantity squared. If we follow a bunch of algebraic steps, if we expand and collect and do some more work, we will actually get this expression right here. These two expressions, the one I'm circling and this one here, actually equal each other. Now, you might say, well, how can we just take your word for that? So we're going to show you over the course of 6 handwritten slides that those two expressions are equal. The way we're going to do it, we're going to expand out this top expression, we're going to expand out this bottom expression, and you're going to see that they actually equal the same thing. Okay, so again, expanding out this circled expression right here, we get what you see written in front of you. And then expanding all this out, doing our expansions, and doing it again here, and doing it again here, we get some terribly long terms, and we get the expression that you see in front of you. And so that top expression a few slides ago, the one circled right here, the one that I'm putting a check mark next to, that actually equals what you see circled in green. Now let's expand out the bottom one. Go back a few slides. We're going to expand this one out. When we expand that one out, we get what you see in front of you here. It's terribly long and drawn out. Unbelievably long and drawn out. But when you collect your like terms, you actually get what's circled in blue. And it's the same. So I think that you'll be willing to acknowledge that the statement that I'm circling at the bottom of the screen is actually true. They both expand to be the same. So if we go back to where we left off, this was the most recent type slide that I was circling, and I had checked this one and we expanded it out, and I checked that one and we expanded it out. We showed that they equaled the same thing. So now we've shown that the magnitude of A cross B quantity squared is equal to this expression. Well, if you look, this first part, that's really just the magnitude of A quantity squared. And this part here, that's really just the magnitude of B quantity squared. And this second part here, that's really just A dot B. And so we've really got the magnitude of A quantity squared times the magnitude of B quantity squared times the expression A dot B quantity squared. Well, remember what A dot B is. This is the component method of A dot B. But remember what A dot B is. A dot B is actually magnitude of A, magnitude of B cos theta. And since we're squaring that expression, we've really got the magnitude of A squared, magnitude of B squared, cos squared theta. So what we've got is that the magnitude of A cross B quantity squared is equal to the magnitude of A squared times the magnitude of B squared minus the magnitude of A squared, magnitude of B squared, cos squared theta. We can actually factor out the magnitude of A quantity squared and the magnitude of B quantity squared. From here we'll be left with 1, and from here we'll be left with negative cos squared theta, which we show here. But remember, one of our trig identities tells us that 1 minus cos squared theta is sine squared theta. So we have the magnitude of A cross B quantity squared equaling the magnitude of A squared, magnitude of B squared, sine squared theta. That means the magnitude of A cross B is equal to the magnitude of A, magnitude of B, times the sine of theta. But remember what we said earlier. We said that that was equal, we said that the area of the parallelogram formed by A and B was equal to the magnitude of A, magnitude of B, sine theta. So what we actually showed was that the area of the parallelogram defined by A and B is actually equal to the magnitude of A cross B. And this expression right here is going to be useful for us in many application questions, including torque. Now, you might be wondering, how can I be so certain that if I know that the magnitude of A cross B quantity squared is equal to the magnitude of A squared, magnitude of B squared, sine squared theta. But how can I be so certain that when I square root both sides, I don't have to worry about any negatives, any plus or minuses making them not equal to each other? Well, the magnitude of A cross B cannot be negative. The magnitude of A cannot be negative, and the magnitude of B cannot be negative, so we're safe there. And because theta is the angle between two vectors, it has to be a number between 0 and 180 inclusive. So the sine of it must be positive, because the sine of an angle between 0 and 180 inclusive must be non-negative at least. So we can determine a square root without worrying about any negative numbers. So if you were concerned about having something squared and then square rooting it and having to worry about plus or minus, you don't have to worry about that in this circumstance. So what we've been able to show, just to summarize, is that the area of a parallelogram defined by the vectors A and B is equal to the magnitude of A, magnitude of B, sine theta, or alternatively is equal to the magnitude of A cross B. And similarly, the circled thing that we have written here, that the magnitude of A cross B is the magnitude of A, magnitude of B sine theta. That will be something which will be useful for us when we talk about other application questions, including possibly torque. Okay, and we'll get into some other of these questions in our lesson.